Okay, so we're talking about modeling, and the type of modeling we're talking about is population growth, where y is some function of time, and it's something to do with population. And it says, the change in the population with respect to time is equal to some constant times of population. And what I do is I go through separating the variables over here. Well, what we do is a pretty easy problem to do, by the way, and you get a pretty simple solution to that problem, a general solution to it. What I want to talk about is if I were to use different letters. All right, and what I'm going to do is over here, write this over here, that P is population, is a function of time. And I want to point out its population is a function of time. So at any given time, you're going to have a population. All right, now what about the population? Well, I know that P, I'm going to call it P now, is greater than 0. We have a population. And what I'm going to say is, in a simple model, is that the change in the population with respect to time, I'm going to say has something to do with the population times some constant. And I'll put this over here, times k. All right? Then what I'm going to do over here is separate the variables. And what do you get? You get dp, 1 over p, equals k dt. I'm going to integrate this guy, and when you integrate it, you get something not too bad. Put this over here, and I say the integration of 1 over p is just a natural log of p. All right. Now, someone says, why are you putting not the absolute value on it? P is a positive number. I don't have to worry about that. Let's do the other side. What are you going to get there? You're going to get kt plus some constant of integration. Now, this is the part where students often get confused. And what I want to talk about is that at t equals 0, something's going to happen to this problem over here. And c is going to actually equal the natural log of p. All right? And that, what's that going to be? I'm going to point out that p0, right, is going to be the initial population. And that's at time equals 0. All right, let's go through this now. I'm going to write this over here. Again, we got the C is a little confusing at this point. So what do you get over here? I'm going to solve for P. What do you get? You get P equals E to the KT plus C. All right? I want to keep going. I'm looking at that. I want to just kind of simplify this a little bit. Write this over here. I'm going to say P equals E to the KT times E to the C. All right? What I'm going to do now, I notice that E to the C will be another constant. And I'm going to call it P equals, I'm going to just simply say, oh, it's another constant. I'm going to call it C star. I'm not sure what it is yet. E to the KT. What I'm going to claim over here, P is now a function of time. And what's it going to be equal to? C star times E to the KT. Now, K is a parameter, T is time. I still don't know what C star is. So what I want to do, I want to take this initial condition, and I'm going to call P0 P0. All right, let's write this down. So P0 equals P0. What's that equal? C star times E. Well, if T equals 0, I get E to the 0. So now I know what the C star is. C star, because C to 0 is 1, is P0. So I got my function now. PT, I may not know what K is, by the way, is equal to P0 times E to the KT. All right? So this is our differential equation solved. Right? The only thing I don't know is K. We have to figure K out. All right? Thank you.